podcast. Okay, well, let's get started. Thank you very much, Koon Young, for presenting your research at this last LCN seminar for this year. So thanks a lot. So it's my great pleasure to introduce Koon Young, who's a reader in polymeric materials in the Department of Aeronautics. He's the head of the Future Materials Group, which sounds very exciting, and is focusing on the development, engineering, and manufacturing of nano-cellulose polymer nanocomposites, surface and interface engineering, and particle stabilized emulsions and foams. So really great to have so much nano in these future materials, and he will tell us about enhancing materials properties with nanocellulose. Please feel free to put questions in the chat or raise your hands at the end of the talk, and we can have the discussion. But first of all, thank you very much, Koon Young. I'll switch off my camera, and the floor is yours.
Thank you. My name is Koon Young. I'm from Aeronautics, as well as I'm affiliated with the Cross-Faculty Institute for Molecular Science and Engineering at Imperial College London. So as mentioned earlier, my research activity is quite vast. Today I'll be focusing only on enhancing materials properties with nanocellulosic materials. So in this presentation, I'll briefly go through why are we interested in upgrading materials or waste materials and waste materials as a resource, and why are we interested in a nanocellulose specifically, and what did we do over the last 8 years or so to utilize nanocellulose in various advanced materials. And ultimately, before we end, we'll talk about whether we actually need nanocellulose or not. So we go back to, is nano really useful? So the main aim of our research mainly is to solve the big plastic waste problem. So we need new materials that are fully recyclable or made entirely from renewable resources that could biodegrade on demand. More importantly, we also needed materials from these renewable resources that actually have the mechanical performance of commonly used engineering materials. Now, you have two methods of achieving this. You can get a very competent chemist. You chain the chemist next to the laboratory bench and force the chemist to synthesize or identify pathways to synthesize renewable resources-based engineering materials. Or you can take a different approach whereby you take existing materials, you combine them together through a composite approach to achieve the same performance as commonly used engineering materials, but these composites are now derived from bio-based resources. And why are we interested in that, and what do we actually think about the whole idea of circular economy and sustainability here? So you have your basic biorefinery concept there, whereby you take biomass, so waste, tree leaves, tree trunks, or even anything that's bio-derived. It captures carbon, put it through a biorefinery, you produce biofuel, electricity, or bio-based materials, such as polylactic acid, for example. You will then use the materials, you then recycle the materials, turn them back to carbon dioxide, water, you grow more trees, you capture the carbon again. What we would like to do is to introduce a second loop there. So you have your biomass, goes through biorefinery, produce biofuel, electricity, or bio-based materials. In the extraction of that biomass through the biorefinery process, you actually generate quite a lot of waste materials, waste fibers, even coming from other industries as well, which we wanted to combine these waste materials with a bio-based materials to produce durable, very, very durable materials that you can recycle back into the process, combined with fresh virgin bio-based materials to create, again, equally durable materials, recycle it back as many times as you can. So we wanted something that's very durable. And when the time is right, you then digest, degrade them, producing more CO2, and all the CO2 is being captured by trees that you're planting, effectively closing the life cycle loop. So So this view here is to keep your carbon in that durable materials loop for as long as possible, such that we have more time to actually grow more trees to capture more carbon. So you're using materials as a tool for carbon capture and storage here. And we achieve this essentially by creating very durable, high-performance materials through a composite approach. For those who don't know what a composite material is, essentially you have two distinct materials, a fiber and a polymer matrix. So the fiber acts as provides parallel strength, stiffness, modulus. The matrix protects the fibers, and the contact point between the fiber and the matrix is what we call the interface. There are two spelling there. It actually refers to separate things, but for the sake of today's argument, it's just the contact point between the two phases. So the picture on the top right-hand side corner there shows you a plant fiber embedded inside a polymer matrix, and the gap there, it should be a proper contact point, and then you will have an interface. If there's no contact point between the fiber and the matrix, then you have very poor interface there. So fiber as the reinforcement, matrix as a material to protect the fiber, hold the fiber together there. Now, creating composite materials out of waste or renewable resources, is that actually new? The answer is actually not. So back in the country that no longer exists anymore, so East Germany, they actually created a car, one of the world's first recycled car. If you think about it, the body of the car is actually made out of cotton fiber from Soviet Union military uniforms. And the whole thing is actually embedded inside a phenolic resin, creating this cotton reinforced phenolic resin composite. You can actually still find this car if you go to the right people there, and that product is extreme. That car hood, that whole product is extremely durable. If it actually exists already, so what can we do differently to make better renewable materials? This is where the nano aspect comes into play. So let's look a little bit of at wood and cellulose. So you have trees, so we go from the top left-hand side corner there. So you have trees which you debark the skin, and you get wood. And wood typically has a performance of about 5 to 15 gigapascal, strength of 50 to 120 megapascal. Not extremely exciting, but it's good enough to be used as construction materials. If you zoom into wood further, you actually get down to the cellulose fiber scale. So this is actually at the center here. So this will be where you would start making your textile fibers. For example, you would dissolve this cellulose fiber, which can then use to make textile fibers, or use it as it is. You can then create paper out of it, or paper cardboard out of it, or boxes out of it. And the length scale here is about 20 to 30 micrometers. Now, this cellulose fiber is actually not the ultimate ending length scale. You can actually refine it further down to the bundles of cellulose fibrils, which you can then refine it further to the elementary building block, the cellulose microfibrils. And if you refine cellulose microfibrils further, if possible, you get to the cellulose molecule. Now we'll stop at the cellulose microfibril scale. And in that sort of bundle of cellulose fibrils or cellulose microfibril, the width is somewhat between 15 nanometers and 3 nanometers, depending on how you refine them. The Young's modulus, or the tensile modulus, in this case E, is between 100 and 165 gigapascal, so that is stiffer than glass fibers. And bearing in mind, these are 3 nanometers, 15 nanometer fiber. The strength of these fibers was measured or estimated to be up to 6 gigapascal by researchers from the University of Kyoto about 5 years ago. So again, this value is very, very comparable to glass fibers. So the whole research in nanocellulose is actually to try and explore these high performance nanoscale fibers, even though the terminology is actually quite confusing, but I'll get to that in a bit. But these sort of 3 nanometers, 15 nanometers on the nanometer scale cellulosic fibers as reinforcement for polymers. Now, I mentioned earlier that the terminology in the field of nanocellulose is extremely confusing. People have been using terminology such as cellulose microfibrils, cellulose fibrils, cellulose microfibrillated, nanocellulose, cellulose nanofibers, and so on and so forth. So for today's presentation, we will focus on the terminology nanocellulose to refer to a family of cellulose fibers in the nanometer scale. So all the width of fibers that is in the nanometer scale, anything between 3 nanometers to 50 nanometers, we'll call this nanocellulose without referring to the source of nanocellulose. And going to the source of nanocellulose, you can actually obtain nanocellulose from different sources. So you can start from wood, which you then convert that to pulp. You pass it through, you refine them through high pressure homogenizers, ultra fine grinders, or microfluidizers. And you get what we call a grade of nanocellulose. So on the bottom right-hand side corner here, that essentially is the nanocellulose themselves that you're looking at. So the scale bar is 300 nanometers, and the individual nanocellulose fibers there are 5, 10, 20 nanometers or so. For the sake of argument today, in today's presentation, wood-derived nanocellulose, we will use the common terminology cellulose microfibrils to describe. Now, I know it's the whole thing is in nanoscale, but why are we using micrometer terms to describe? Again, this comes from the convention adopted by the paper industry, whereby anything that is below cellulose fiber scale, it's called cellulose microfibrils, and then the next scale down is essentially the cellulose molecule. So we will use this cellulose microfibrils to describe nanocellulose derived from woody biomass that are in the nanometer width scale. Okay, good. You can also make nanocellulose by sugar. Scientists failed to polymerize sugar to a very large degree of polymerization, but bacteria does it for us brilliantly. So you have bacteria typically from the Comaggai Acetobacter species. It eats nutrients, typically sugar or sugary-based materials. The bacteria is extremely happy and it starts to produce nanocellulose for us. That picture on the top right-hand side corner is actually how the nanocellulose looks like, produced by the bacteria. If you take a closer look at that, actually is a nanofibrous, is a fiber network consisting of 50 nanometer, very, very uniform 50 nanometer with cellulose fibers, and this thing is chemically pure, 100% pure cellulose. The cellulose microfibrils, again, nanocellulose derived from wood, they are not chemically pure. They typically contain what we call a hemicellulose in there. Bacterial cellulose here, it's actually pure cellulose without any other impurities. Very, very crystalline, 90% degree of crystallinity as far as we can measure. There are hypotheses that confirms that most likely bacterial cellulose is 100% crystalline. So there's still quite a big dispute there on the crystal structure of cellulose, cellulosic materials here. In any case, we shall now refer to nanocellulose synthesized by bacteria as bacterial cellulose today. Okay, nanocellulose derived from wood, so cellulose microfibrils. It's I can think of the fact that we have so much trees in the world. The pulping industry is really thriving at the moment. And we can make a lot of these nanocellulose from wood. That's great. But growing bacterial cellulose, is that even possible on a commercial scale? And the answer is yes, you can. If you're at Imperial College, you would have gone past by Earl's Court. There's a street in Earl's Court that sells Asian food. You can actually buy bacterial cellulose from there, and it's actually edible. So they actually manufacture bacterial cellulose on a commercial scale, but as a food product. as nata de coco effectively. And if you don't really want to buy this, you can actually grow this at home. All you need is a starter culture from SCOBY, so symbiotic colony of bacteria and yeast. You can grow your own bacterial cellulose. So essentially sugary water, the starter culture, you leave it there for a couple of days or weeks, you get your bacterial cellulose out. So you will find these tea in the supermarket nowadays. It's called kombucha tea. So what people do is they drink the tea, throw away the bacterial cellulose. We have professors in Sweden that has been growing this and drinking the tea, and they have tons and tons of these things at home, not knowing what to do with it. And our research is to take those and develop materials out of it. So back in 2014, the Chemical and Engineering News magazine actually raised the question, nanocellulose, what can we do with these materials? And our approach here is rather easy. We wanted to use very simple design to our product, to our materials, that will incorporate manufacturability such that it is easily scalable, and the incorporation of nanocellulose in a clever way will lead to radical effects being observed in the performance of the final product, which then will lead to higher commercial uptake. So I'll take you through some of the research that we have conducted over the last couple of years here. So an interesting feature of nanocellulose is this thing called hornification. Most common materials, when you dry them, you remove water, you produce a dry cake, powdery materials, which you then dump it into water again. You should be able to redisperse them in water. Cellulose from paper works up to a certain extent. Nanocellulose is very, very difficult to achieve that reversibility in redispersion. So here's a picture that demonstrates that. So you have wet nanocellulose. In this case, we're using bacterial cellulose as a model here, but the same thing works for wood-derived cellulose microfibrils. You dry them, you get a piece of paper, a dried piece of nanocellulose. When you soak this nanocellulose paper back into water, it doesn't go back to this state. Instead, it will stay as this piece of paper for as long as you can observe. So we have soaked papers like this in water for about a year now, and it still stays as water. The reason is because when these nanocellulose are at such a small length scale, 50 nanometers, 15 nanometers, or potentially even 3 nanometers, depending how the degree of refinement that you have put the cellulose through, the surface area between the nanofibers is huge. So as you dry them, you have so much hydrogen bonding that forms in between the nanofibers that even if you dump it back into water, it just wouldn't rehydrate anymore in this case, just because of the hydrogen bonding that's being formed between the individual nanocellulose fibers in this case. And that is actually one very peculiar aspect of nanocellulose. And it actually makes nanocellulose extremely difficult to be reproduced. If you think about any materials that we use, engineering materials that we use, that are typically in the dry state. So if you try to put this into a dry material, you will lead to drying and hence agglomeration. You need to process the materials wet, but at the end of the day, you have to evaporate off the water. So you're processing 1 kilogram of wet and dry materials with 99% water being evaporated. So your production rate, real production rate, is actually extremely low in this particular aspect. But what we can do is to utilize nanocellulose hornification to our advantage by using the nanopaper as the reinforcement for our polymers. So this is the thesis of Alba, who actually investigated nanopaper as a useful building block. So what she essentially did here is to take that dry nanopaper. So you take the wet gel, you dry them, and you dry them easily by pressing and drying. You can do this at home with a simple panini press or even a simple iron. You can do that. And you then laminate this paper with an epoxy. In this case, actually, it's an acrylated epoxidized soybean oil, sorry for the mistake there, not soapy bean, but soybean oil. And then you polymerize it that way, and you actually, surprisingly, you should get a relatively transparent material out of it. And here's the microstructure that you can see. What is more interesting here is that the just the nano paper alone, so the paper, the consolidated paper made out of nanocellulose, the drying ones, has a tensile modulus of approximately 20 gigapascal. So not as high as the 165 gigapascal single fiber value, but 20 megapascal actually stems from the 165 gigapascal of the single fiber there. And this material, this nano paper, actually has a strength of approximately 180, 190 megapascal there. Your polymerized soybean, also polyazo, it's a very weak and soft polymer matrix. Just by introducing this nano paper at 40%, 50% volume fraction, you're able to push the performance up to about 7.5 gigapascal in modulus, approximately 100 megapascal in strength. And all this comes from the fact that your nano paper is now carrying the load, and bearing in mind that the nano paper here is the reinforcing phase, and the performance of the nano paper comes from the performance of the nanofibers, along with the high degree of hornification in this case. Now you may wonder, well, there's only one single layer of nano paper. It's not extremely useful there. Well, actually, you don't really need to use a single layer of nano paper. You can actually stack multiple layers of nano paper together to build your structure from a 100 micron thick film to a couple of millimeters thick composite structure. So that's the thesis of Martin here. So what he did was to have a nano paper of different grammages. So this one would be a piece of nano paper that is 50 grams per square meter. So areal density or grammage, essentially a measure of how much mass of cellulose per unit area. Or you can actually make the papers in such a way that it is 25 grams per square meter, and you put two of them together, so the overall cellulose content within a composite is still 50. Or you get 5 of the 10 grams per square meter, which then you also have 10 grams, 50 grams per square meter in the final composite, or 10 sheets of 5 grams per square meter nano paper stacked up together. So overall, you have 50 grams per square meter of cellulose nanopaper laminated with polylactic acid as the polymer matrix. And in this case, the way you manufacture them is to stack and you press, as simple as that. And here's the microstructure that you can see. So in the context of just looking at the bottom right corner there, you have 50 grams per square meter. So you actually see your polylactic acid sandwiching your nanopaper inside. Again, if you have two pieces of 25 grams per square meter nanopaper, so you see the nanopaper with the polymer matrix, and you can extend this to 5 sheets of the nanopaper or 10 sheets of the nanopaper there. So the nanopaper gets thinner and thinner, but the overall mass of cellulose per unit area of composite stays the same at 50 grams per square meter. If we look at the tensile performance here, so the green bar, green column, recommends a tensile modulus which corresponds to the left y-axis. The tensile strength, which is represented by the hollow icons, refers to the right y-axis here. So on the x-axis, there are the different configurations of composites that we produce. The loading fractions varies between 40 and 50%. Here, in all cases, the introduction of the nanopaper will increase both the stiffness or tensile modulus and tensile strength of the resulting nanopaper-PLA composites compared to neat PLA. Again, this is because the nanopaper themselves actually has a modulus, the high modulus and high strength stemming from the performance of the individual nanocellulose fibers themselves. So we are able to achieve a tensile modulus of approximately 10-11 gigapascal and a tensile strength of roughly 100-110 megapascal there. In addition to making these laminated composites, we are able to utilize this nanopaper structure as a reinforcement to create transparent materials for impact protection. So that's the thesis of Daniela here. So that piece of plastic there, hopefully you can see that, is actually a piece of cellulose nanopaper impregnated with a transparent resin, a UV polymerizable resin. So that piece of plastic there is a nanopaper reinforced resin of approximately 50 micrometers in thickness. We then laminate this in between impact modified acrylic. So this thing here has two transparent impact modified acrylic sandwiching that transparent film in between. So this whole structure here is 3 millimeters thick, and it's still transparent at the end of the day, as you can see either from this picture or from the transmittance versus wavelength graph, where within the visible light, you still have a transmittance of roughly 80%. The interesting bit about this is that if you were to look at the Sharpie impact strength of this product here, you are able to, just with the introduction of the cellulose nanopaper into the final transparent composite, we're able to increase the impact performance by 60% relative to the properties, the impact properties of impact modified acrylic, bearing in mind that impact modified acrylic is already designed to have high impact performance, and we're able to push that value further up by 60%, all with just introduction of 0.2% of this cellulose nanopaper into the final product, just 0.2%. And that allowed us to push the performance up to almost 20 kilojoules per square meter, compared to impact modified acrylic of about 12 kilojoules per square meter of impact strength there. Now, we talked about nanopaper as a useful material structure, but what else can we do with nanocellulose, particularly utilizing the hornification effect to upgrade properties of materials, particularly waste materials? We did this with natural fibers, so you have loose natural fibers to start off with. So typically you would then compound that with a polymer to create a natural fiber reinforced renewable composite, for example. But what we did here was to use bacterial cellulose once again as the binder to bind these fibers together. So the process is rather simple. You disperse fibers in water, you add a small amount of these nanocellulose. In this case, we're using bacterial cellulose to start off with. You'll filter away the water, essentially dewatering, and then you press dry them at 60 degrees Celsius. So design is rather simple. Nanocellulose, in this context, bacterial cellulose, and some sort of loose fibers here, which in this case is sisal fibers, natural fibers. Put them together and it binds with each other. The manufacturability aspect is the fact that it's a simple paper making process or wet laying process. So it's nothing fancy in terms of manufacturing. You filter and then you press dry them and you get a natural fiber with bacterial cellulose as the binder. So on the bottom here, you have about 10% bacterial cellulose binding the whole sisal fibers together. This middle picture here doesn't have bacterial cellulose, but rest assured that it is very, very soft and very, very weak. You that it is about to fall apart. The key thing here is that we don't actually need any polymeric binder in the sense of fossil-derived polymeric binders to bind loose fibers together in this aspect. Now, to demonstrate that without bacterial cellulose is not good, so there's a picture here with an empty plastic cup. And we did it in a simple 3-point bending demonstration. So this is your loose sisal fibers. We just press them together with just a little bit of water in there. The whole thing flexes again because it doesn't have any rigidity associated with the final structure. With 10% bacterial cellulose, without water, again, nothing moves. But when you add it all the way up to 80% of the plastic cup, it still doesn't bulge at all. This is 170 grams. We managed to do this experiment with a pint of beer, so with a glass pint of beer as well, and that mat doesn't even bulge or deform at all. And we can actually create a very big preform system, not just limited to small scale experiment. So this thing is a 30 centimeter by 30 centimeter, 1600 grams per square meter bacterial cellulose bound sisal fiber preform, which is bigger than the head of this poor PhD student there. And if you were to look closely at its morphology, you can actually look at the sisal fibers there. Those are the bigger fiber that you see. And these are the bacterial cellulose network. So they are not your 50 nanometer, but they're 50 nanometer agglomerated together, forming that network that you see. You can regard them as your mini nano paper, if you will. So it sort of stems across the natural fibers, holding the whole natural fibers together. And the reason is because these natural fibers are actually hydrophilic. So it loves the bacterial cellulose, and the bacterial cellulose loves them. So they will stick together with each other, and they will extend their reach to the adjacent sisal fibers, and then they hold them together, forming the network, binding the sisal fibers together. And that's a close-up of one of these surface of the natural fibers that you can actually see the bacterial cellulose nanofibers on the surface there, well hornified, well bound together. We measure the tensile index. Again, tensile index it's a paper industry test standard. Essentially, it's the force per unit width of a sample, mainly because the area is not well defined. So using megapascal is actually not a very relevant unit for describing tensile properties of these sort of rather porous materials there. In any case, without bacterial cellulose, there's no tensile index, so it doesn't sustain any tensile deformation or whatsoever. With 10% bacterial cellulose, you actually achieve a tensile index of 12.5 kilonewtons per meter. So that bacterial cellulose provided rigidity to a sisal fiber preform that it never had before. So that bacterial cellulose is really indeed useful by utilizing its hornification effect that binds the whole fiber network together. We can actually take that preform that you have seen before. You can infuse that with, again, with soybean oil. In this case, we were using Luprox P as the initiator. We polymerize it at 110 degrees Celsius. We post-cured it at 130 degrees Celsius. At a fiber loading fraction of 40%, we are able to see a big improvement in modulus just by introducing sisal fibers alone. But with that added 10% bacterial cellulose, so you have a nanocellulose enhanced natural fiber reinforced polymer composites here, you are able to push the tensile modulus up further from about 3.5 gigapascal to almost 6 gigapascal in modulus, just with that 10% increase introduction of bacterial cellulose into the system. Similarly, in tensile strength, you observe the same trend as well. The introduction of that bacterial cellulose and nanocellulose into the system pushes the tensile strength up to of the final nanocellulose enhanced sisal fiber reinforced polymer composites in this case here. Now, you may ask, I've been talking about nanocellulose all the time without making reference to whether it's bacterial cellulose, mainly bacterial cellulose, but no reference to wood-derived nanocellulose, in this case, cellulose microfibrils, acronym CMF here, or pulp fibers. So the question here that we ask ourselves is, do we really need nanocellulose here? And the answer is yes. So we repeated the experiments with different types of cellulosic materials. You have your typical bacterial cellulose that I've shown. You have the wood-derived nanocellulose that you have seen. And now we have micrometer-sized pulp fibers as well. In all cases, pulp fiber doesn't increase the tensile index of the resulting preform. In this case, the preform is the flex fibers rather than sisal fibers here. And you can actually see why on the morphology here. So you have your your flex fibers here with the nanocellulose sort of coating the surface and then forming the beautiful network. In the case of pulp fibers here, you have your sisal fibers, that three fibers will be one element, one size of flex fibers here, and your pulp fibers are of the same order of width, fiber width, as your pulp fiber. So you actually don't have that surface area to try and bind or cover and bind all the sides of the flax fibers together. So that leads to the lower mechanical performance. So you do need the nano aspect here to push the amount of surface area up to lead to more irreversible more number of irreversible hydrogen bonds between the fibers, essentially better honification in this case. And we have a Dyson, in this case, Royal College of Art student who then took the idea further and go and create bespoke art pieces made out of waste fibers, which is sold for a very expensive price in Taiwan here. And last I heard, these products might be coming to Marks and Spencer as they are showcasing pieces on how they are contributing to sustainability in this particular aspect. Now, chicken feathers. So we consume a lot of meat, poultry meat in this case, and a lot of these chicken feathers are essentially going to landfill incineration, or you send it out, or you hydrolyze it to create feather meal. So can we do something about it? So this is a collaboration with a startup company out of Imperial College, Aero Powder, to create insulation. So we took some of the fibers and we worked with them, and Victoria here actually came to me one day and said she loves chicken feathers and want to do something about it. So we formulated a project for her on chicken feathers here. So remember natural fibers here, previously they are all hydrophilic. So the cellulose will bind to the natural fibers beautifully. Chicken feathers, on the other hand, are rather fluffy, and they are rather hydrophobic as well in this case. So we have to modify our manufacturing process. Initially, we didn't think it would work, but it turns out that it will. So we started with pulp fibers. We dispersed pulp fibers with chicken feathers with 50-50 IPA water solution there. And there's nothing, we can't measure anything out of it. But with nanocellulose here, we are able to measure something out and something rigid here, and a significant increase in terms of tensile index. The reason that it works is because the nanocellulose, due to its high surface area, actually encapsulate the chicken feathers rather than binding the individual feathers together. Feathers are nanocellulose network due to the nanocellulose honification effect in this particular aspect, and that piece there is a dried piece of cellulose microfibers, or nanocellulose in this case, and you see the bulb of the feathers there as well. What we did there was then impregnate these feathers with gelatin. You actually produce something of a decent mechanical performance, which we can use for an extended period of time, after which you would dissolve, recover your gelatin, recover your fibers, and you can start all over again. So there is a possibility of creating materials that you can use, dissolve, and you can make the preform again to your liking, allowing you to essentially close the loop, if you will. Now, I did mention a point whereby do we actually need nanocellulose in this aspect? So this is where Jana, my PhD student, started her thesis on. Essentially, the idea is that if I have pulp fibers, I refine it, but I don't go all the way to produce isolated nanocellulose fibers. I produce enough such that my nanofibers are still attached on the surface of my micrometer-sized fibers. Now, what would that do to us? So we call these fibers hairy fibers for now. So we don't go all the way through in the context of refinement to isolate the individual 50 nanometer fibers. We just let the 50 nanometers stay attached to the micrometer fibers, micrometer-sized fibers there. We create paperboard out of it, in this case 600 grams per square meter paperboard. What we observed was that with increasing refining time, we actually reduce the porosity of the final paperboard, and that leads to an increase in increase in the time required for air, a volume of air to pass through. So in this case, air permeability, you should regard this as the higher the number, the longer it takes for air to pass through. So our oxygen transmission rate decreases down to 4,000 cubic centimeter per square meter per day. Our water vapor transmission rate stays the same. So that actually opened up some sort of possibility for us to use paper as some sort of packaging material for some sort of application that requires water vapor transmission, but not oxygen transmission. We're still exploring here at the moment. The mechanical performance of these materials, again, scales beautifully with the refining time. So the green hollow icons represents the tensile modulus on the left y-axis. The blue dots represents the tensile strength on the right y-axis here. So with increasing refining time, you actually increase the modulus and strength of the final paperboard beyond conventional polymers. Even PLA has a modulus of only 3 gigapascal and a strength of about 70 megapascal, and we are able to just produce something that is comparable or even exceed that. Nothing more than dumping pulp fibers into a simple double disc refiner, refine for a small amount of time to make these hairy fibers. You make a piece of paper out of it, and you get this sort of performance there. Right. To quickly sum up, so nanocellulose or cellulose in general will help us develop renewable materials. And the problem with cellulose is nanocellulose is that it's actually extremely hydrating. So one way to get around this hydration problem is to make nanopapers out of it. And you will see a couple of examples. You had seen a couple of examples there where nanopaper can be impregnated with a resin to produce a nanopaper reinforced polymer composites, or you can use these nanocellulose to bind these loose fibers, feathers together, producing a rigid fiber preform there. And in many cases, we don't need to go down to the isolated nanofibers in this particular respect. We could actually just live with the fact that you have the nanofibers attached on a microfiber surface and use that as one of our building blocks for let's call them nanofiber enhanced microfiber reinforced polymer composites or reinforced materials with this respect. With that, I think I'll end my presentation here. Thank you for listening, and obviously I would thank all my funders for funding all these projects here. Thank you very much.